Okay, let's do this. Hi, so when I was first visiting Penn, I took this picture 5 years ago. I was in an Uber and I was so excited because I was visiting campus for the first time. So I was trying to sneak this picture and it was kind of really awkward, but I did it. And little did I know that just a few years later, I would be out on that exact same bridge with sometimes a broom, a dustpan, and even our trusty vacuum named Vincent in hand. Now, when we're out on the roads like this, we're looking for something called road dust. It's all that gunk that accumulates on our streets. And as it turns out, this dust has a bigger story to tell about the other side of vehicle pollution. When we think about vehicle pollution, we often think towards things like fossil fuel emissions, and for good reason. That's a major concern for decades, and we've been making great strides in addressing it. However, there's an invisible pollutant that we've been missing a little bit, and that's what I searched for inside this road dust. They're tiny little particles made from rubber, tire wear particles. These particles are made from whenever we drive. So every time we get in a car, whether we turn, whether we accelerate, whether we brake, our tires begin to shed these tiny little pieces. But they're not just rubber either. Tires are made of synthetic polymers, so they can be classified as microplastics. And they're actually one of the most abundant microplastics in the environment. Further, they have a lot of toxic additives, some of which have been linked to massive salmon die-offs in the Pacific Northwest. That means these little particles are becoming a major concern for environmental and human health. And as we know, cars aren't going anywhere anytime soon, so it's up to us to begin thinking comprehensively and address the full scope of vehicle pollution, including our tiny particles. So today, let's uncover what really happens after rubber meets the road. Now, to get there, we had to do some interesting types of field collections. It involved late nights, early mornings, even intense rainstorms. My lab mates and I, over the time of it, decided that we were Philadelphia's road dust ghostbusters, and we were doing our civic duty by helping them clean up the streets. Along the way, we got a few strange looks, but with every sample that we collected, it brought us closer to questions that we needed to answer. Things like, where are these accumulating, and in what amounts? We looked at over 15 different sites, and in every single one of them, we found these tire particles. And we found them in massive amounts. Let's just take Walnut Street Bridge, for example. We have one sample, and we found 0.3 grams of tire particles in it. Now, I know this might not sound like much, but when you consider that our bridge is 128 meters with accumulation on both sides, and our sample spot was just a 1 meter square, over a week, we accumulate up to 80 grams of tire particles. Now, in a single year, that 80 grams can become 9 pounds. So one bridge in one small city, 9 pounds of tire particles. Globally, our tire particle emissions reach 6 million metric tons. So that means this number we see right here is a really, really tiny fraction of our greater pollution problem. So we know that on our bridges, on our roads, there are these massive amounts of tire particles. But it's not just the amounts that we are worried about, it's how they behave in the environment. See, unlike other microplastics, they travel differently. Some settle in our soils, some can float along our rivers, and some are even prone to things like resuspension. And this is because tire plastics have a wide range of densities. So we wanted to investigate that a little further. That included going into our lab with some of our particles and running density separation tests. By using density solutions of varying densities, we can actually separate the weights of our tire particles and assign them by extracting what's floating and what's sinking to specific density ranges. Now, what we found was striking from this. At all of the streets that we were looking at, so things like the really high traffic roads like Walnut Street Bridge, or our quieter streets, maybe more residential areas, our density distribution was strikingly similar. This means that whatever is affecting the density of our particles is happening consistently across all of the sites that we have, not just at one specific way. So what actually controls our TRW, or our tire particle density? Well, in order to figure this out, we had to start looking closer, and I mean literally. This means using instrumentation like this, known as an electron microscope, at the Singh Center for Nanotechnology here at Penn. We were able to use instruments like this to see our tire particles at microscopic levels and begin doing things like assigning elements to where we see the particles on. Now, this is used a lot in material science, but for tire particles, it was a little new. And for pairing these tools with our image analysis method, we were actually able to develop a novel tire particle characterization way of actually seeing what's on our tire particles and why they have varying densities. So real quick, let's put this to the test. On the screen are two different particles. One is going to be our low density particle, and one is going to be our high density particle. Now, before I tell you which is which, take a moment and try and guess. All right, you got it? Let's see. So the one on your left is going to be our low density particle. The one on our right is going to be our high density particle. And as we take a closer look, we see here on our high density particles, there are things that seem embedded or encrusted covering our tire particle. And those are the things that actually alter the density of our particles. That means these types of particles are going to be more prone to settling in the environments they land on, whereas our low density particles are going to be more prone to traveling down our rivers, floating through the air. Now, this understanding of how our tire particles interact with our environment is crucial because it allows us to understand how particles transport and flow through the environment, and it'll ultimately lead us to designing solutions to mitigate their impacts. So I know I just said a lot. So from here, maybe you're asking what's next. Well, for our policymakers in our cities, we really need to start recognizing tire pollutants as major urban pollutants. And we need to integrate them into our environmental regulations. But honestly, I would just love to see Philadelphia do a little more street cleaning. But I don't mean to go out there and do it myself with my vacuum. For our tire industries, though, we need to continue pushing innovation. Right now, researchers are studying things like self-sealing tires, tires that can recover from some amounts of wear. However, we need to keep pushing things like this new types of materials that'll allow us to have tires that last longer, but also release fewer harmful particles and create less environmental damage over time. And for all of us, well, awareness is just the beginning. Most people don't know that their tires are polluting the environment, but now you do. And as you share this with other people, I hope they'll start learning about it too. You can start supporting policies that are addressing these tire pollutants and encouraging things like smarter urban transportation planning, making sure that cities are more walkable or have better transportation for people to take. And finally, even the small things like maintaining tire pressure can all reduce tire pollutants over time. So, now that we know what happens after rubber meets the road, it's up to all of us to rethink how we drive, design, and regulate for a cleaner future. Thank you.